Good morning. My name's Tom. I'm just hosting, so just doing a quick introduction for Rob. Hopefully everyone's in the right room. There's been a few room swaps, so if you're not here to talk about M3 and Prometheus, you're probably looking for app dev, which I have no idea where it is. Nobody's leaving, so we'll get on with it. So today we're going to hear from Rob about M3 and Prometheus. I was on the program committee and was super keen on this talk. Mainly mean I'm one of the Prometheus developers, but I also develop a competing system to M3, and I really want to hear about how they've solved some of the same problems we've had to solve. So, give a round of applause for Rob.
Cheers. Thanks, Tom. So yes, this talk is called M3 and Prometheus, monitoring at planet scale for everyone. And other than the clickbait title talk, I'm going to talk a little bit about monitoring an increasing number of things. So yeah, there's a few people in this space and technology products now, as Tom kind of mentioned. Metrics is being used as a platform more than ever. It's becoming really a foundational building block, similar to how databases serve applications for products. Metrics are being essentially a building block for building reliable systems at scale and delivering high levels of service quality. And it's also, being used for auto remediation, auto rollback. It's being used for auto balancing, stateful systems. It's becoming pretty prevalent. Like if you look back, 5 to 10 years, I think logging was far more popular than metrics, and that probably still is the case. But metrics now has a pretty strong foothold in observability. I also want to talk a little bit about operating in many different regions, many different environments. That's becoming increasingly more common these days, especially A, because it's easier to do with the cloud, and B, because it makes a lot of sense for a lot of different businesses. And of course, the talk itself is going to focus on M3 and Prometheus. So who am I? I'm an Australian monitoring node, self-proclaimed, of course. And I've commonly found that I'm drowning my friends with pictures of my kid, so thought I'd do the same here. Also the creator of M3DB, which is an open source time series database, and that is essentially the underpinnings of M3, which is an open source monitoring system built at Uber, which I've been working on for about 3+ years now. And I'm a member of Open Metrics. We're a CNCF committee that's trying to standardize a metrics exposition format so that a lot more of these systems that are being built in the community can talk to each other basically natively using a shared kind of standard. So Prometheus, just as a reminder, this is the first talk of the day, and I'm going to talk about M3, which is solving different things. Prometheus is what most organizations will reach for and should reach for when they begin wanting to monitor their stack and starting to build alerting and other kind of auto monitoring systems at their companies and organizations. It's an all-in-one industry standard solution. Essentially will both discover and ingest and allow you to store and query metrics. And you can think of it similar to kind of like MySQL in that it's very much built to be rock solid and run on a single node. And you can set up different types of deployments of it, but that's primarily the space that it's trying to solve. So, as a reminder, Kubernetes looks a little bit like this in most people's lives. So essentially, you have a Prometheus instance, maybe it's in a single region. It's usually, of course, a single Prometheus instance can only be in a single availability zone because it's a single instance itself, and it basically monitors your application as it runs on, say, Kubernetes or the EC2 Amazon platform or GCE. So basically, the rich service discovery layer allows it to kind of understand how and where your application is running very easily and basically discover and collect those metrics and make them accessible to you for visualization using Grafana and also using Alert Manager or some other alerting engine. So M3, what is that? That is, it's a project from Uber. began in early 2015, so kind of 6-9 months or so after Prometheus itself. And it was built primarily to scale monitoring horizontally. So it was kind of orthogonal, at least in the early days of what it was trying to do. And pretty much still is. Again, Prometheus is what every organization should reach for first before any of these other systems, because it solves so many of your problems, issues, and is interoperable with everything out there from day one. And most people don't have that many metrics, so even running 2 Prometheus instances will serve a whole bunch of organizations just fine. But M3, for those that it doesn't solve, that setup doesn't solve so well, is essentially, yes, built to scale your monitoring horizontally and in a very cost-effective nature. So that's one thing that from day one has been very, very important for Uber. Some organizations, it's very easy for it to happen. It happened to us, it happened to Netflix, it happened to tons of other companies. Your monitoring and observability platform, especially when engineers start to instrument absolutely everything they possibly can, begins to be a large part of your cloud footprint, essentially, and ends up costing you a lot. So Uber has been able to push, that percent of spend of your entire stack for monitoring down to roughly 2%, up from larger organizations. Sometimes you see 10, 15, 20% being spent on monitoring, observability, and reliability at companies and organizations. So, that's always been a staple of the project and will continue to be one of the goals going forward. And it was essentially first released in open source in August 2018, so about 8 months ago. My math is probably wrong on that one. Long flight is my excuse. Anyway, it's basically been written in open source from 2016, but we only really put together the documentation and other stuff to actually run it with integrations with things like Prometheus and that since August last year. So we have monthly community meetings with attendees from small to large organizations. It's released every few weeks, and also last night as I was basically trying some things out that I realized didn't quite work right. So, this is kind of what it looks like. It's basically multi-region aware, so it can basically store metrics local to each region that you run in, and then essentially fans out queries when you need to join data across those to all of the regions that you run in. And so, it understands Prometheus and understands Graphite, and is kind of compatible with multiple metrics formats, which for Uber was really important when we got started, because we basically had a whole bunch of legacy applications that emitted Graphite metrics. Still to this day do. They're becoming a smaller percentage of the overall footprint of applications at Uber, but they're still there, and we didn't want to turn them off or run multiple disparate systems just for the different types of metrics formats that we supported. So 3 main points I want to talk about M3. I just want to basically talk to how it runs pretty much anywhere these days, which is great for, I think, the open source community, whether you're running on premise, whether you're running in the cloud, whether you're running on Kubernetes, it runs there. And it also supports monitoring a whole bunch of different applications. It's scalable to billions of metrics. This is a workload that's been run in production at Uber for quite some time now. And it has a focus on simple operability. We, to this day, only have 2 dedicated SREs on the M3 team at Uber, which is pretty incredible considering it went from tens of storage nodes to thousands of storage nodes today. So touching on runs anywhere, so as I mentioned, similar to Prometheus, because it's basically compatible with Prometheus as a remote long-term storage, you can monitor kind of any application that's cloud native or has a service discovery layer in Prometheus. It runs on Kubernetes or on-prem, as I mentioned, and it's multi-region aware. So that's pretty important, I think, as we're kind of running these more complicated applications everywhere, to be able to be natively multi-region is important. So why would you want to use M3 with Prometheus? So a lot of people are wanting to kind of establish SLAs of their companies and organizations in a way that lets them really be data-driven about what they're monitoring, how they're performing, and a lot of the time that means storing things for longer. So you can basically do month-on-month comparisons, or even just getting started week on week. So you can store metrics at very specific retention periods, and you don't have to worry about losing 1 or 2 nodes or backing up or restoring data or anything like that. As long as you always have at least a certain number of replicas available, you'll be able to access and read and write your data just fine. And you might also want to store different types of metrics at different retentions, which is becoming increasingly important. And you can scale up your storage by just adding nodes. So this is, again, what Prometheus may look like with your application. This is what using it with M3 might look like in a very basic manner. So we're still looking at a single region in this example. Essentially, M3 Coordinator is a proxy tier that ingests Prometheus remote write requests, which is HTTP1, snappy encoded protobuf. And so you can actually put an HTTP load balancer in front of M3 Coordinator and send a whole bunch of different Prometheus metrics just at that layer of M3 Coordinator. So it's kind of stateless unless you're aggregating metrics. And what's nice about that is that's really the only 2 roles you need to run to get started. The M3DB cluster itself, which you can manage with Kubernetes, is the second role here, and that's spread across availability zones. So as soon as a metric crosses the threshold from Prometheus into the M3 system, it's replicated across multiple availability zones. And so what a lot of people, of course, are interested in doing is viewing kind of all the metrics from multiple Prometheus instances across either in a single region or across multiple regions. And if you want to do that, essentially you can point Grafana or your loading engine directly to the M3 Coordinator. It does speak PromQL natively and essentially can join all that data that you're sending from the different Prometheus instances because it's stored in one place. So you can do a sum across regions or a sum across wherever your application is running. And you don't have to worry about, oh, does my Prometheus live here for this application in this zone or region? And then, you can also deploy a dedicated M3 query instance. Why you might want to do this is so that you basically don't interrupt your writes when heavy read queries come in. So, sometimes people like to look at thousands or hundreds of thousands of metrics and perform crazy aggregations which might cause a problem for query services of any kind. So these poison queries are able at least to be isolated to the read path and don't disrupt your collection of metrics if you deploy a dedicated M3 query instance. So talking a little bit about Graphite, we support basically Carbon TCP on ingestion and Graphite functions. We're trying to work with some of the Booking.com engineers to see if we can basically use their Graphite query layer. Right now it's essentially something that is home-baked and based on the 0.10 release for Graphite. So it's not as up-to-date as the most recent Graphite. The full set of functions are just not quite there, but it's great for getting started, and hopefully we can work with Booking.com to get that into a much more complete set of Graphite query support. So this is kind of what it looks like with Graphite. Carbon TCP line protocol can be adjusted by the coordinator, and then essentially you can store Graphite and Prometheus metrics in a single cluster side by side. So this is quite nice because, again, if you're coming from like a legacy system, you've got your latest and greatest, but you also want to support Graphite, you only need one single system at least to store and query that data. So M3 runs in a multi-region aware fashion, as I kind of mentioned. Essentially, there's zero cross-region traffic running where you store all your data basically region local. This is pretty important because, as a lot of you know, like cloud bandwidth costs are very, very real. It's one of the more expensive parts of actually running in the cloud. And shipping traffic cross-region all the time can be very expensive. So the other thing that's nice as well is that people basically would like to have high reliability. And that's one way of getting around that is essentially like spreading data across regions, or at least like a single place. That's something that M3 supports, at least locally in a region, is just persisting data across availability zones. So if you have a single availability zone that goes down, you're still reading and writing metrics just fine in that local region. You can lose an entire region as well. You'll still be able to access data from all other regions in both the read and write. And this is what basically a region local deployment of M3 looks like. There's essentially a Prometheus that sends remote write data to M3 coordinators, which are stateless in your availability zones. And then the M3DB cluster, as I said, is spread over availability zones managed by Kubernetes. And then the global query tier looks something like this, where you can essentially put a HTTP load balancer in front of all of your regions, and then essentially queries can hit either any region. So if one goes down, it'll fall out of the load balancer. And because the coordinators or dedicated M3 query instances, if you're deployed using that, because they know about each other, they basically will sum and aggregate data from all the other regions and return you a single sum in one query. So talking a little bit more about the kind of core pillars of the system, which is scaling to a very, very large number of metrics. Uber has 4,000 plus microservices, which is both a tyranny and also not a tyranny. It's a let builders build mentality, essentially, is what we call it. So there's some nice things that comes from just having a whole bunch of microservices and making it easy to deploy, but it is definitely a nightmare at times. So, because of this, it forced us to basically make systems that made everything look the same and scale out basically infrastructure underneath those microservices in a very horizontal fashion. So one of the benefits of this tyranny is essentially there's no onboarding to monitoring. There's no provisioning of servers for a team. You just add storage nodes as required. And it's used for a whole bunch of different things. So at first, it was just the standard kind of application metrics, latency, request counts, etc. But then we started realizing that developers were using it for business metrics as well. So, as anyone that's used a Prometheus client library knows, very easy to begin to just drop in instrumentation in tons of your code paths. And so it's not meant to be relied upon for business making decisions, but it's very easy to get an idea of how your application is basically performing in a different market segment if you can support high cardinality metrics at the storage layer. And then we also collect basically network fabric metrics, so bandwidth and latency for different network devices and routing systems, data center device temperatures. We do capacity planning off these metrics for basically buying hardware for some of our on-premise data centers, working out how much load their load average is, how that's increasing, and we can look at that month over month, and that helps us. And we can also do like macro analytical style queries to see like disk failure rates and different types of disks in different SKUs. So actually being able to store and query these in a really large fashion is really, it becomes extremely beneficial, especially as you do, especially as things are getting more complicated. And we also do a whole bunch of stuff that I never even knew about. There's a whole bunch of people using us as a platform, basically for syncing data into it and then reading that data out to load balancer applications. And so, some of these stateful things are built on Apache Helix or other kind of infrastructure, which basically means they move data around as workloads move. So the M3 platform itself, it's obviously has to support a large amount of users. We basically see around 700 million metrics being aggregated by the system at peak capacity, and then that translates to roughly like 35 million metrics stored at any given time to storage. And this is across thousands of M3DB nodes, and there's about 9 billion metrics in use at Uber. So it's architected, for reliability and scale. That's really where we started and why we started there. That was the fundamental underpinnings of this project. Each component is designed to run across availability zones and region, and there's low inter-region network bandwidth. Queries are executed and distributed in parallel. So one of the biggest things when you start to get to the billions of metrics is being able to find these metrics and find them quickly. So because of the flat collection that basically any metrics platform does, you don't write a schema. You don't tell your metric system how to basically store and index different types of metrics. So essentially you need to build a very generic indexing system. And when you have flat structure like that, being able to find metrics at very large high cardinalities becomes difficult. So basically here you can see that we distribute the work of at least finding those metrics and extracting that data to many multiple storage nodes. And this essentially happens in parallel as you execute a query. So as you kind of like continue to get a larger amount of this flat structured data spread across everywhere, being able to distribute that metric lookup starts to matter a lot. So this is opposed to other types of systems that basically archive data to long-term storage. So they might offload it to S3 or other like slower moving data warehouses. And this is actually a great pattern. I think that for some people works really well. But because it's a little bit perhaps easier to manage. But having said that, Kubernetes and Kubernetes operators are making things a lot easier these days. But one basically downside of this is that when you go to really large sizes of data sets, essentially you have to rely on a single process to be able to pull all that data and find all those metrics in the index lookup for a given query. So you can imagine that once you get to a certain size for a time window, a time slice in retention that you're looking at, that's a lot of data to pull back and for a single query node to basically perform that lookup and find the data you're looking for. And so the index, talking a little bit more about that, is basically backed by FST segments. This is similar to what Apache Lucene uses to index documents, and which of course Elasticsearch is built upon. It essentially allows us to filter and regex queries over billions of metrics. We are using, we've made some upstream changes to the Go Couchbase Vellum library, which provides this. So we didn't build this from scratch. This is a very powerful library and definitely very interesting. So basically, an FST segment though kind of looks like a trie. You can imagine if all the words that or all the text that you're basically indexing is put into a trie, and then it basically compresses that trie and collapses that, and then you can basically very efficiently walk that trie and work out essentially which parts of the trie match that query, and then return basically the union of all of the matching trie nodes that you match for a query. And then we have a focus on, again, as simple operability. Again, there's only 2 SREs on the M3 team that is managing all of this. Basically, it can run on premise, but also on M3DB. And what makes a lot of this able to be run easily is that basically we have automation that can replace nodes for you, add or scale up or scale down, depending on what you need. And so, we've kind of pushed for these fewer roles and pushing complexity into these roles themselves. So again, you only really need 2 roles to get started with M3. We don't have any background tasks that require monitoring. We used to have a large batch downsampling that we would do where we basically write, raw metrics into our system, then have some batch process come, collect some of those raw metrics, compact them into 1-minute or 10-minute tiles, store them back. So when you're storing metrics for months or years, just collecting them at 10 seconds and then trying to read all of that 10-second data in one query is not really very efficient. You're just operating on gigabytes and gigabytes of data. So downsampling that into 1-minute or 10-minute tiles is very important. One thing we found, though, doing it in a batch fashion, reading aggregated data that we stored and then writing it back, is that you basically have to babysit this process that goes and does this kind of like large batch processing job now. So we basically in the M3 Coordinator, and if you're running in a more scaled up fashion, you can use M3 Aggregator, which is a distributed aggregation server. But basically, we do all that downsampling on the ingestion path. So essentially, this happens in real time as you're collecting your metrics. So as long as your instances are healthy, you're fine, and you don't kind of have to babysit these background tasks. So that's one differentiating factor, I guess, with M3, which is interesting. And again, the Kubernetes operator can handle a lot of the replacing and scaling up and scaling down of resources for M3. So I thought that we might have a quick demo of at least some of what it can do. So this is essentially what I'm going to run through now. We're going to basically look at a multi-region setup of M3, and you can try and, I believe it should be fairly reproducible. And this repository that I've linked here basically shows a README on how to reproduce this benchmark. But essentially, we basically got a setup that looks very similar to this. So Node Exporter and Prom, we've kind of compressed into a single benchmarker utility called Prom Remote Bench. And essentially, it generates Node Exporter data using the InfluxDB metric benchmarker generator. So basically, all this data looks like Node Exporter coming in, and it just remote writes that using the Prometheus remote write format. So that's protobuf encoded, snappy compressed over HTTP1 to the M3 Coordinator. And then they will all write it to basically local regional M3DB clusters. So demos always fail, so that I'm prepared for that. And we'll just see how we do. So first steps first is Wi-Fi. And I really should have joined this before stepping up here. Okay, I'm just going to hotspot on that. So basically, I'm going to, let's first look at the EU West zone. So here I'm just going to check in and see basically, okay, so I've basically got 10 of these Prom Bench remote Prometheus benchmarkers running. So each one of these does roughly about 1,000 metrics per second coming from Node Exporter. So I'm just going to port forward to my Grafana instance running here. Okay, great. And that is here. Great. So basically, because I'm running 10 of these, you can see here that translates to about 10,000 metrics per second per node that I'm running. So essentially, I'm running 30 storage nodes. Over those 30 storage nodes, I'm pumping about 100,000 logical writes. Because M3DB replicates that at a factor of 3, that essentially means we're doing about 300,000 actual writes, because after replication, that's how many is being persisted to disk. And so we're ingesting 100,000 logical writes and 300,000 actual writes to this 30 node cluster right now. So basically, I'm going to go and scale this up. So if we edit the deployment for Prom Remote Bench, we can find that, yeah, so there's basically 10 replicas here. I'm going to scale this up to 100. So we should, see all these containers being created. And essentially, okay, so basically now we see extra load from these Node Exporter metrics starting to hit these instances. And so we're going to about 100K per second, up from 10K per storage node. This should be about 1 million writes per second logical and 3 million actual writes, basically including replication. Let's just look at the last 5 minutes. And unfortunately, I'm not using preemptible instances, so this is an inexpensive demo to run. So basically now we're at 100K per node, doing about 3 million actual writes, 1 million logical writes. I'm going to basically scale this up again. Let's take it to 200. Okay, so now we're going to create a bunch more of these benchmarking containers, and then we'll see this load added. So, I'm kind of expecting to get to about, if we can get to 400K, that'll be nice. I'm not 100% expecting to get there, considering I was playing around with this last night. So this is basically a view of the GKE Google Kubernetes engine cluster view. And so this is the utilization across all these 30 nodes. So this is the CPU utilization of the cluster. Now, I'm using 30 nodes here, but there's essentially, the coordinators running on top of those DB nodes, as well as the Prom remote bencher and some other things in the cluster, like etc.d and stuff like that. So it's not just M3DB using these resources either. So here, we can see basically CPU is definitely starting to spike up a not insignificant amount. Okay, so that seems pretty stable now. And we've hit about, 6 million actual writes with 2 million logical writes. So now we're going to scale up again. And if we get here, I might stop, because I prefer to do Q&A than just make you watch graphs all day. But basically with benchmark, that's definitely doing 4 million actual writes. So that's about 2x from kind of what we're seeing now. This dashboard as well, by the way, can be found on grafana.com. So if you find yourself playing around with M3DB and you want to actually see some of the stats coming out of it, you can find it there. And so, yes, now we're at 300K, doing, basically 9 million actual writes, 3 million logical writes. You can see the server-side latency creeping up here. This is basically P99, so most of the writes are completing much faster than this, but it's definitely it takes a little while to kind of warm up. So it may have been probably not a great idea to ramp this up so quickly. Anyway, I'll take this to 350, but then I'll take questions. So so that's that. I do want to jump back as that's going to there and basically talk a little bit about the roadmap. Basically we want to add further lifecycle management to the Kubernetes cluster. So we basically want it to make it support a lot more of the day-to-day management activities. We want to add M3QL query language support, which is an internal query language at Uber that is pipe-based, which we think the community may be interested in. And then, we're also going to be looking into making it a more generic time series database. But I'm going to basically take questions now, and thank you all for listening. Really appreciate it.
Hello. I had a question about the ingestion path. You mentioned something about being able to downsample. I was curious, what sort of control do you have on exactly what you decide to store in terms of what's coming in?
Yeah, great question. So essentially we have some standard retention policies. So basically like 2 days at 10-second resolution, 30 days at 1 minute. And that basically applies to everything that we're collecting. And then essentially we have the ability to just make API requests or use the UIs, like not quite there in open source, but essentially to create filters. And then developers just go in and create the filters themselves. And essentially that means you can kind of store things at arbitrary resolutions. We have resolutions retention up to 5 years at 1 hour resolution, scaling all the way down to 1 second resolution at like 24 hours or something like that.
Folks, please stay seated until the end of the talk. Respect the speaker. Anyone else got another question? Go on, one more. Thank you.
Thank you for your talk. I have a question about one of the scheme you mentioned when we use M3 Curer and we point Grafana to it. Which protocol does support M3? Is I understand right that it is a PromQL like Prometheus format?
Yeah, so the reason we have only begun talking about that right now is because yes, it does understand native PromQL. However, it's never going to be one-to-one as accurate as default Prometheus. So it's because it's been developed recently. It's still basically being worked on, but it supports pretty much all the functions in Prometheus today. There is, I think, some issues with binary. Some of the operators aren't working 100% as expected right now. And we actually need to build basically a comprehensive test suite that ensures that it acts exactly as Prometheus does. So that's still coming, but yes, it basically speaks PromQL as well as Graphite as well.
Yeah, here. So one of the challenges of scaling Prometheus is, of course, at storage level, and that's a great solution. I encountered issues on the memory level, meaning that with not a huge Prometheus that I'm managing, like 2 terabytes of data, I'm exploding in memory. So I'm wondering which solution did you implement, or would you recommend for this kind of?
Yeah, great question. So one thing is essentially memory is always going to be an issue on a lot of these systems. Some of the reason why we get such high compression on this data and allows you to really reduce the cost is that you're basically doing very, very high levels of runtime length compression on this data, which is a lot easier to do when it's stored in memory. So you'll see systems like basically M3 has a similar issue. It uses a fair amount of memory depending on the block size that you choose. You can make that block size smaller, but it makes your queries take more time because it's basically searching more blocks on disk. But essentially, we would like to get to a point where we're kind of not really doing regular compactions, because that's what we're trying to avoid with the system and reduce the cost overall, but this kind of concatenation compaction process with M3. So hopefully at some point we'll be able to actually unload some of that's not being touched very frequently, but we're not there yet.
Thanks very much, Rob.
Cheers. Thanks, Tom.